Hello, everybody. I'm starting my stream here a little bit early. I'll um, I'll wait till 4 o'clock till I do anything substantive. I just want to know everybody know that I'm Mark Weitzman. My YouTube channel is Theoretical Physics with Mark Weitzman. This is sort of a semi course that I'm running with on Piazza Group Theory in Physics. Um, Piazza is a site where I host almost all of my material. I have 3 sites on my Piazza, and once you sign up, you can post things, questions, and read other people's and read my announcements. Then I have like a resources page where I have a lot of stuff, my videos that I've made on the topic, as well as this one's on group theory, as well as a lot of notes that I've made on some textbooks. And then this is an actual textbook that's hard to get online, so I've put it here. The Texas file is quite large. I got it off the Internet Archive. Trying to get myself centered here. Um, and it's sort of typed and handwritten. It was self-published. It's an amazing book, but I'll talk more about it when I get to the lecture. These are my own latex notes that I'm making in the book that are compressed by about 50%. I'll talk more about that. And this is the book that I'm talking about. I got this off the Internet Archive. This is my own copy. It's sort of like falling apart, as you can see, and it's gotten a lot of use over the years. Going back to my Piazza site, I have 2 other sites. My main site is called Topics in Theoretical Physics, and here on the resources page, I have like just all the links and everything that I've found useful over the years. Could be video links, it could be notes, anything I've had on just about all topics in theoretical physics. And, you know, the other site I have is another course that I'm developing that I'm very far behind on, and it's Quantum Field Theory: A Student's Perspective. Over the years on this course, I've gotten a lot of questions and everything. I think I have about 500 people enrolled in this course and 500 on the Topics in Theoretical Physics site. But the group theory site is new, and so what is it saying? I have about 23 right now. Anyway, so you can watch the videos and then get more detail, a lot more detail on the site. Um, I have a new microphone, by the way. I hope the audio is better than it's been in the past. This is supposedly a very fancy USB microphone, and hopefully is picking up the sound much better than it's a SHURE, something like that. So that is what I'm looking to. I'll get started here in about 3 minutes. Um, there's I used to do a lot of MOOCs online and everything, and I've been staff for some of them. Um, 8.05x is finished about a few weeks ago, and it always takes a while to load. I don't know why, but I was the moderator on the discussion forum for this course. This is the second of the very good and advanced quantum mechanics courses at MIT. Sometime this year, probably 8.06 applications of quantum mechanics will run. The book out of the course claim a textbook published by Barton Zybock, and here it is. So the idea 8.06x will probably be coming up soon. I do not know when. And another MITx. This is all on the new site, MITx Online. Hopefully you're all familiar or getting familiar with this site. These used to be run on edX, and now they're run on MITx Online. Some courses are still being run on edX. Another course that's just finishing up right now is course on vibration and waves. And one of the things with the group theory is that I hope to get to this course is finishing up. I think the final exam is just ending. And then there's another course starting in a couple of weeks. It's taught by Jim Freewicks of Georgetown University. His quantum mechanics course just ended, but he has a I'm not going to be able to find it, but he has a mathematical methods course at about the sophomore level, and it should be starting in about 2 days, I think. So you might want to look. This is on edX, Georgetown University, Jim Freewicks. You might want to look at that if you need help with some mathematical physics. Now, okay, so it's 4 o'clock, so welcome everybody. Today, as I said, I want to continue group theory in physics, and I want to continue with Schensted's book, which is an excellent book, and covers a lot of things that you don't find elsewhere on the symmetric group and Young's diagrams. And so let's begin. Let's begin by reviewing and picking up where we ended last time. So we had group representation. And this is, a lot of times you'll hear like group theory in physics and everything, but what physicists are really, theoretical physicists, are really interested in is group representations. Because group representations act on linear vector spaces, and they act on linear vector spaces, and that's where like quantum mechanics takes place and everything is in a Hilbert space, a linear vector space. So okay, so I have some remarks about the sound is very good. Thank you very much. And so we're really interested, for the most part, in group representations, and in a while I'll explain why. But let's just review what it is. Let's say we have a group, call it G, and in these lectures, for now, until a little while, I'm always talking about finite groups. And if we have the group representation, this is a set of square matrices of the same dimension that act on a vector space usually, but not always, complex. Sometimes we deal with real vector spaces. And so we're looking at that. And the main thing is that if we have the following, if A and B are in G and AB equals C, this is the group multiplication, this implies that gamma, and gamma is what we're going to call the matrix that represents the group element A. This implies that gamma of A, gamma of B is equal to gamma of AB. That's what we mean by a group representation, and this is also equal to gamma of C. And the gamma matrices need not be distinct. And like, for example, the most trivial matrix is gamma. Gamma of A is the identity matrix on, let's say, n dimensions for all of the group elements. This is clearly a group representation. It's what we call the trivial representation. We just represent everything by the gamma matrix, and this over here is trivially solved. So that's like one example. But if they are distinct, we say the representation, and I'll usually abbreviate rep by REP, is faithful. Usually we find in physics that often we find in physics that we have like 2-to-1 representations, like spinors. In the rotation group, the relationship between SU2 and SO3. Now, when we have a representation, the first thing we want to check is it reducible? And so a reducible representation is one where the form of gamma of AJ, is equal to what we call block diagonal. And this happens for every matrix in the group. It's not just one group element. It's all of them have a particular form. I'll call it like gamma of A let me go back to AJ here. I don't know why that didn't erase. AJ. And then here will be like big fat zeros. And then we'll have like a gamma B of AJ. This is what's called a reducible representation. Because basically what happens is, and these don't have to have the same dimensions, but it's block diagonal. This could be like 3 by 3, and this could be 2 by 2, and these will be rectangular. But it basically splits the basis elements for the vector space, let's call it S, into two I don't want to use the word grouping, into two sets, let's say, that don't interact. If you were to think of this like an operator in quantum mechanics, the matrix elements between one set and the other set would be 0. And you can keep on reducing. Oftentimes these themselves will be reducible, and you'll get And you'll get something like zeros everywhere, except on the diagonal you'll have like gamma A, gamma B, gamma C. And this is for all group elements. So this is what a reducible representation is. And when we have a reducible representation, we like to get it in this form. An irreducible representation is one I had a comment last time about my handwriting, and yes, it is terrible, but I'm 67 years old right now, and it's not going to change. But I'm not the first physicist with terrible handwriting, but still, that's the way it is. But anyway, so if you have a irreducible representation, it means it can't be block diagonalized. Now, in a sense, you can't always tell. You can't just look at a matrix like, let's say, look at several of the things and say, okay, this isn't block diagonal, because the basis elements aren't fixed. You can diagonalize any given matrix. I can, if it's a Hermitian matrix, which this is not, but if we have like a Hermitian matrix, I can diagonalize it so that it might have the form 3, 4, 1, but only for maybe one group element. I have to do it in order to block diagonalize. I have to do it for all the group elements. So anyway, the irreducible representations, these are the building blocks for all finite, say for all the representations. If we know the irreducible ones, the reducible ones are just irreducible ones stacked up. Okay. Now, so let me ask and answer a question that I alluded to earlier. I'm sorry. Why do we care about all these representations? This is a question that confused me. I remember studying quantum field theory, and I was like, well, okay, I understand the symmetries of the rotation group and everything, but why don't I just use the group elements with the rotation group? What does it matter? Why do I care about whether it's a spinor representation or a vector representation or a scalar representation? I was a little confused. And there's a very simple answer for that, and I'll just review why right now. So some of you may have, some here may have a good knowledge of tensors. Okay, if not, just think of matrices. Let's say we have a 3 times 3 matrix or tensor, and we're working with symmetries under the three-dimensional rotation group. Okay, well, let's so imagine we're taking the what we do in quantum mechanics. We take what's called a direct product, but you can just think of it times. So 3 times 3 is 9. We find out that it breaks up into like 1 plus 3. This is a direct sum. Don't worry about the details of this. Plus 5. So what does this mean? Well, the 1 means that there's a component, we call it a scalar. Also, it's the trace of the matrix, which transforms by itself. It's just a one-component object. When you start studying quantum mechanics, for instance, you'll have the wave function, and it's just a one thing by itself. Later on, you'll do spin, and you'll get two-component objects, and so on. The 3 is like a, you can represent it as an anti-symmetric matrix. And it's sort of like isomorphic to like a vector. And then the 5, this is a symmetric, traceless matrix. And it's often used to represent, like in electromagnetism, quadrupoles. Now the point is that these things don't mix. You can treat them separately. And what's more is they have different degrees of freedom. The scalar has 1 degree of freedom, the vector has 3 degrees of freedom, and the quadrupole has 5 degrees of freedom. Different degrees of freedom means you have different equations. Differential equations, let's say, for various degrees of freedom. So that's why this is all important. And saying something has rotational symmetry or spherical symmetry doesn't mean it's a scalar. It could be a vector, it could be a quadrupole, it could be a second-rank tensor. So that's where group theory is very important. In quantum mechanics, you come across this right away. When you look at, for example, angular momentum, let's say either orbital or spin, you have things like a spin 0, like particle, is a scalar, or field is a scalar, and it has 1 component. Spin 1/2 has it's called a spinor. It has 2 components. And then you'll have like a spin 1 vector. You'll have 3 components. Usually the rule is 2j plus 1, where j is the total angular momentum. Then you'll have like you even have, sometimes you'll study like for spin 3/2 particles, like right? Schwinger, they have a famous equation. This has like 4 components. Then spin 2 tensor. For spherical, it's going to be 5 components. Okay, so that's the sort of why, in case you were wondering. Now, I think, briefly mentioned last time, and I'm going to go into more detail here. My cat wants to be fed right now. The smallest non-abelian group is of order 6. That's the number of elements it has. And it's known as, call it either D3 or S3. They're isomorphic. The D3 is the dihedral group. And in this particular case, that just corresponds to the symmetries of an equilateral triangle. And with S3, it's just the permutation group on 3 elements. So, if you think of an equilateral triangle in the plane, let's say it has vertices A, B, and C. And let's say this is the center of the triangle. And if you remember your Euclidean geometry, the medians and the perpendicular bisectors, or certainly for an equilateral triangle, they all meet at one point. We'll call it the center of the triangle. And we have the symmetries. That's my cat scratching over there. I don't know if you can't quite see him. Anyway, we have the symmetries. The first symmetry is the identity element, do nothing. So I either use E or E for the identity element. Then we have an element C, which is a counterclockwise. Let's call this line over here L1, L3, and L2. Counterclockwise rotation of 2 pi over 3, 120 degrees. C bar is a clockwise of 2 pi over 3, 120 degrees. And then we have sigma 1, sigma 2, sigma 3, and these are all reflections about, L1, L2, L3. So if we were to flip like sigma 1, you can see how this group is isomorphic to the permutation group. If you imagine labeling the triangle as ABC, now we were to flip it about this axis, B would go to C and C would go to B. So this would go to A, C, B under sigma 1. And then under, let's say, under C bar, I'm sorry. I don't know why it doesn't erase. Under C bar, clockwise rotation by 120 degrees, A would go to C, C would go to B, and B would go to A. So you can see that you could think of it as it's amazing. Excuse me. I don't know. For those of you who have these devices that listen, like Google, whatever, I didn't say anything near like, hey, what that. So I don't know why that started speaking. So you could think of these as permutations or symmetries in the plane. And Schensted, I'm not sure I'm pronouncing her name right. By the way, she passed away a few years ago. I think she lived to the age of 95. She was married to a mathematician. She herself was a prominent theoretical physicist, and she lived in New England, and she was at the University of Michigan, and she retired to Florida, and she self-published some of these books along with her husband. So, and they did really good work on a lot of areas of discrete mathematics and theoretical physics. So she calls this group GB, and there's a multiplication table. Usually, when you have like a group, you can small finite group. You draw yourself a multiplication table. And you put like elements, you put the elements of the group, E, C, C bar, sigma 1, sigma 2, sigma 3, and on the top, same thing, E, C, C bar, sigma 1, sigma 2, sigma 3. And then you fill in, like I'll fill in one row here, C bar, E, C, sigma 2, sigma 3, sigma 1, and then this is C bar, E, sigma 3, sigma 1, sigma 2. What's important is what's called the rearrangement lemma. I don't want to call it a theorem, let's call it a lemma. But for groups, what happens is every row of a group is just a reordering of the elements of the group. You can never have two elements of the group, one in the same row or in the same column. You have to have, they all have to, it's just a reordering. And this enforces the inverse property and the identity property of the group. Associativity you have to check separately because this doesn't guarantee associativity. Now, I'm going to try and, so this is Schensted's book, and these are my notes, and you can see that here I have the whole group table filled in case you have, it's easy to calculate, and here's another picture. So, also, and this is right out of her book. I just copied it in my notes. My notes are just complete. I don't want to say plagiarism because I'm not going to publish it or anything like that. Somebody's asked for recommendations for books. I'm going to tell him very simply. Feynman Lectures on Physics. There's nothing better. They're available online. Just type Feynman into your Google thing. Here they are. Volume 1, Volume 2, Volume 3. This site from Caltech also has his tips on physics, his excellent Cornell lectures that are well worth watching. You can have the lecture recordings, the photos, the notes, original course handouts. And if you go to the original lecture, you can get problems and solutions. And if you go to Volume 1, let's say, and you look at, let's say, I don't want to scare you. I'm going to give you an easy topic, theory of gravitation. There's an outline of the lecture, and then there's Feynman's lecture notes. And it's all beautifully typeset and everything, all corrected. There were a significant number of small mistakes in the original course, and you can get just from the top-notch, one of the top theoretical physicists in the 20th century, and this is a great way to learn physics. Otherwise, any of the standard textbooks that, there's so many of them. I learned from Halliday and Resnick, Advanced Placement Physics. But I recommend the earlier editions. They've been dumbed down a little bit. Physics, PA, Parts 1 and 2. That's what I studied for AP Physics. And but I highly recommend the Feynman lectures on physics. On my sites on Piazza, I have all kinds of things where I give recommended books, and I have like a whole playlist of about 20 lectures on books for theoretical physicists. I think so it's on one of my sites. Anyway, I want to get back to my lecture here. So in her book, these are 6 representations of the groups. These are the group elements, and these are the matrices that correspond to the groups. I call them, she calls them, gamma. And like I said, I've copied from her notes. I'm not plagiarizing because I'm not trying to pass it off as my own work. But I've cut down her book, which was, half handwritten and half typed. I cut it down by about 50%, just for myself, so I can get the essence of it, and it makes it easier for me to review. But the first representation here is the trivial representation. As I said, you assign the number 1 to every group element. The second representation is also a one-dimensional representation, and it's what they call the permutation. The word's escaping me all of a sudden. Anyway, this is a representation which assigns 1 to every even permutation and -1 to every odd permutation. So that's another representation. Every permutation group has this, assuming it's a dimension higher than 1. Now, gamma circle 3 is a 2-dimensional representation, and I actually have these matrices. And you can check. You can multiply this matrix by this matrix, and you should get whatever EC bar is. You can go back to this table and say, what's EC bar? It's C bar. Obviously, the identities thing, and so on. So this is another representation. And then I have 3 more representations, which I'll discuss shortly. There are an infinite number of reducible representations. You can always keep stacking irreducible representations in various blocks, but some have more importance than others. So in this table, I'm going to go back to my iPad now. In this table, gamma 1 circled, 2 circled, 3 circled are irreducible, and it's not obvious. The one-dimensional representations are obviously irreducible, but it's not obvious that the two-dimensional representation is irreducible. These are the irreducible representations. of GB. And they're the only irreducible representations of the group GB, which is equal to isomorphic to D3 or S3. So, and you might notice, this is hard to see, but it's a very important theorem that we'll discuss next time. This is of dimension 1. This is of dimension 1. And this is of dimension 2. And notice that 1 squared plus 1 squared plus 2 squared is equal to 6. And this is going to always happen. This is the sum of the irreducible representations in the groups of di squared is equal to n, and n is the order of the group. Number of elements in the group. So the first three representations that were on that page are the irreducible representations. Gamma 4 is a three-dimensional representation. And if you look carefully, I'm going to go back to that page. If you look carefully at gamma 4, you'll see that it seems to be gamma 1 stacked up with gamma 3. You notice this block over here is over here. There's always the 1, 1, 1, 1, 1, 1. So this is equal to gamma 1 plus gamma 2. That's the reduction. That tells you it's reducible. Gamma 5 is also a three-dimensional representation, and what I said before is that it's reducible. This is known as the defining representation for S3. And what it is let's say you take a typical matrix like 0, 0, 1, 1, 0, 0, 0, 1, 0. If you define, like before I had like A, B, C, let's say I represent them. I represent A by a column vector, 1, 0, 0. B is 0, 1, 0. And C is equal to 0, 0, 1. And this permutation itself corresponds to C over here. So this is C is equal to. And you'll notice that CA, just using matrix multiplication, is equal to, let's see, it's 0, 0, 1. So I got 0 there. I get 1 here. And I get 0, 1, 0 times 0 is 0. And this is equal to B. So this defines, clockwise, when we did before, I did the anti-clockwise, but if I did the clockwise, I would have, if I did the counterclockwise, ABC under C, A would go to B, C would go to A, and I'm sorry, this is a counterclockwise. A goes to B, C goes to A, and B goes to C. And you can check, so A goes to B is the important thing there. And we have here CA equal B. So these matrices over here in gamma 5, they just implement the permutation group directly. But it's not irreducible. It is reducible. And that's interesting. Gamma 6 is a six-dimensional representation. and it's what we call the regular representation. And this is very, very okay. I'm sorry, I didn't switch back to the iPad. Okay, so I established that CA is equal to B if we represent elements by columns. So gamma 6 is a six-dimensional regular representation. This will play a very important role in the theory. I don't want to go into the definition of what the regular representation is, but the regular representation always has the dimensions of the number of elements in the group, and it always, when you reduce it, we'll prove this later, but when the regular rep is reduced, like in this particular case, we'll find that gamma 6 is equal to gamma 1 plus gamma 2 plus gamma 3 plus gamma 3, which we'll often write this as gamma 1 plus gamma 2 plus 2 gamma 3. And every matrix, will be in block diagonal form. You'll have like a number here. I'll just put the number 1. I'll just put gamma 1 here. Gamma 1 is one-dimensional. Then there'll be gamma 2, which is also one-dimensional. This is for an arbitrary group element. And then we're going to have gamma 3, which is going to be like a box, 2 by 2 box, and then we'll have a repeat of the gamma 3. And what we'll find is that whenever we reduce the regular representation, we end up it contains every irreducible representation, and not only that, it contains it a number of times equal to its dimension. So gamma circle 3 has a dimension of 2. It's irreducible, and it will occur twice in the regular representation. Okay. So I think that's as far as I want to go today. In the next lecture, in the next live stream, what I want to do is I want to cover the major theorems, of, let's call it, finite group representations. And then, and this will include the very important orthogonality theorem. See, what group theory does is, some of you may have had Fourier analysis. And with Fourier analysis, you go back and forth and everything, but Fourier analysis is basically one-dimensional. Group theory deals with symmetries that are higher dimensional because they deal with non-abelian groups, not just numbers. They deal with operators and objects that don't commute. So we need the analog of what Fourier analysis is for multidimensional objects. And that's what these major theorems will give us, and the orthogonality theorem. And we'll talk about characters. Characters and character analysis. So, this type of thing is an example of character analysis. Using the characters of the representations, I can get this decomposition. I don't actually have to block diagonalize every element of the group and see that it works. I can just use characters to get this. And then, so that will finish lecture 3 of Schensted. Like, finish lecture 3 of by the way, Schensted's book, I should have said this earlier, but Schensted's book is 2 courses. One is a short course. See here, it's a short course on the app, part 1, and it's about 60, 70 pages. The rest of the book, part 2, has much more detail and goes much farther, and is about 300 more pages. So she originally published the short course in 1966, and then 10 years later, when the quark model, and this all is like relates to the quark model and everything, it helps understand that. When we had the quark model, she republished it and vastly extended everything to the 360-page book that it is now. So, and then I want to go to lecture 4, which has applications to quantum mechanics. Things like selection rules, perturbation theory, especially degenerate perturbation theory. And then we'll just briefly mention continuous groups. Now, I just want to outline sort of like where we're going. Most books on group theory and physics, like Z's group, and let me just read this remark. Yeah, all these books, there's a lot of good books on mechanics. Taylor has one. Klepner is a little bit more difficult than the average one, but it's good. All of these are good for learning physics and getting, A+ in your college courses if you're there. The Feynman lectures will teach you to think like a theoretical physicist. So I highly recommend also reading those. But what I wanted to add was all of the books like by Anthony Z and Tung and everything, they always start out with finite groups, and there's a lot of important theorems in that. But you might say we don't really use, other than maybe people who do like lattices and condensed matter physics and chemistry and everything, they need all those symmetries of lattices and everything. But for particle physicists, and that's where my emphasis is, and quantum field theory and everything, we're always dealing with continuous groups and continuous symmetries. Groups like U1, unitary group in one dimension, that's for electromagnetism. SU2, spin or weak interactions. SU3, color, gauge theories. And then there's like grand unified, what we call guts. SU5, SO10. Then if you go to string theory, you'll do exceptional groups like E8, etc. But what's interesting about these continuous groups is that they're related to the finite groups. For instance, to understand everything about the quark model and everything, you need to understand all the representations and you need to understand things like direct products. Like if you have a quark might be let's just do like SU3 flavor, the flavor groups, not the color, but things like the top and bottom quarks. I'm sorry. That's a different generation. I want the up and down quarks. This is what the proton, a proton is made up of up, up, down quark, and a neutron is an up, down, down quark. These are the valence quarks. There's a lot more stuff there, gluons and antiparticles, particle pairs, and so on. So I know Tung, not Tung, I can't, his name slips me, but one prominent physicist who has a lot of notes on quantum field theory, he recently gave a lecture where he said quarks are more complicated than the valence quarks. Yes, we know that. But the thing is that so these are what we call the defining representation of SU3, what we call the 3. And the antiparticles would be in the 3 bar antiparticles. But sometimes you combine them. You do things like a 3 cross a 3 bar. And you get something like a 1 plus an 8. So these are like mesons. You may have heard of these things. And scalars. So we need to know how to do things like Clash-Gordon decompositions and products and everything. And to do all of this stuff, it turns out to analyze the general linear group in n dimensions, or the unitary group in n dimensions, or the special unitary, and I'll define these in future lectures, in n dimensions. It turns out that to analyze all these things, the analysis needs the symmetric group. Or the permutation group. So that's the connection between the finite and the continuous groups. And that's why what we're doing right now is fairly important. And so that's all I have to say today. I'll come back next time and we'll continue. I highly recommend, and I'm going to put an end note on this video, but go to my site, this one or the other ones, post questions if you have any, and like I said, all the material is here. An individual asked earlier, who was 17 years old, about how to learn physics, and one thing I would tell everybody is, while sometimes watching physics videos is entertaining and everything, the only really way to learn this stuff is to get yourself a good textbook and verify all the equations and do all the problems. If you have a teacher in a lecture helping you out, that's okay and everything. But all these MOOCs and everything, you really can't learn without the books. Sometimes for very new stuff where the book isn't there, you'll need notes. But I highly recommend digging into the textbooks. So that is all I have to say today. I'm going to stop streaming now. I hope everything worked technically. Sometimes I make mistakes. Gradually I'm improving. I think the sound will be much better this time. And I'm getting used to this OBS and YouTube software. So till next week. Thank you very much for watching. Bye-bye.